The importance of failure repeatability lies in its role in understanding and improving systems, processes, and products. Failure repeatability refers to the consistency with which a system or device can reproduce an outcome under unchanged conditions. In the context of product design, engineering, and testing, being able to consistently replicate a failure means that the underlying cause can be more accurately identified and addressed. Learning from failures. Organizations strive to learn from failures to prevent future occurrences and improve performance. However, learning from failure is not straightforward and requires a nuanced approach. Failures can be categorized into preventable, unavoidable, and intelligent failures, each requiring different strategies for learning and improvement. Preventable failures occur when there is a deviation from known processes or standards. For example, if an electromechanical device fails because a technician did not follow the established assembly procedure, resulting in a loose connection that causes the device to malfunction, this is a preventable failure. Unavoidable failures in complex systems may arise from unique combinations of needs, people, and problems that were not foreseeable. For instance, an electromechanical device might fail due to an unexpected interaction between its electrical and mechanical components under extreme environmental conditions that were not anticipated in the design phase. To learn from these failures, redundancy and robust design. Incorporating redundancy can help ensure that if one component fails, others can take over its function. Regular maintenance and monitoring. Keeping a close eye on the system's performance can help identify potential issues before they lead to failure. Incident analysis. When failures occur, conducting a thorough analysis to understand the root cause is essential. Intelligent failures occur during experimentation when trying out new ideas or technologies. For example, a company may develop a new actuator for an electromechanical device to improve its efficiency. If the actuator does not perform as expected during testing, this is an intelligent failure. The key to learning from these failures is to encourage experimentation, create an environment where innovation is encouraged, and failures are seen as a learning opportunity. Small-scale testing. Conduct experiments on a small scale to minimize the impact of failures. Rapid feedback loops. Implement systems to quickly gather data from failures to inform future design iterations. One common failure in fuel cell systems is the internal failure of the air compressor. The air compressor is a critical component in the air supply subsystem, responsible for delivering the necessary airflow to the fuel cells. Air is required for the chemical reaction with hydrogen to generate electricity, and any fluctuation or interruption in the air supply can severely affect the efficiency and output of the fuel cell system. When selecting a centrifugal compressor for a PEMFC system, engineers must consider the specific requirements of their application, including the desired air pressure and flow rate. For instance, a PEMFC system designed for automotive applications might require a compressor capable of delivering air at a pressure ratio of 4 with a flow rate of 200 liters per minute. The chosen compressor should also be compatible with control strategies that can dynamically adjust the air supply based on varying load demands and operational conditions. The control strategy might involve a feedback loop that monitors the fuel cell's output and adjusts the compressor speed accordingly to maintain optimal airflow and pressure. This could involve using sensors to measure the oxygen concentration in the exhaust gases and adjusting the compressor's operation to ensure the fuel cell operates within its most efficient range. In summary, selecting the right air compressor for a PEMFC system involves choosing a compressor type that meets the system's specific requirements, implementing effective control strategies to ensure the air supply is precisely regulated, and adhering to safety considerations to mitigate risks associated with hydrogen fuel cells.